Am I visible? Okay, yeah, now I'm visible. Okay, I guess everybody's back now to continue playing with Python and physics, more specifically. Um, so before we get back into it today, I wanted to repeat some business-related things. This is a slide I showed last time, but I want to show it again so everybody knows exactly what to do, where to go to get help, and so forth. There's this email up here at the top here. I suggest that you just send a blank email or a blank email to that address, and you'll get something like this as an automatic reply, this stuff down here at the bottom. And it contains all the links that you need to, say, Slack and so on. So a lot of people joined Slack right away after last time's lecture, and there's been a lot of good discussion and activity taking place there. So go ahead and do that again if you haven't done that already. There's a Dropbox folder down here at the very bottom. You see a link to where you can get materials that we're going to put on Dropbox and recordings of everything that we do here. And right here, there's a recordings link that you can look at. So make sure that you don't forget to do that. On the main web page, there's been some updates with links to resources that we've provided. Don't forget that. Some things about QCD, what you need to get started on if you want to do QCD. And we have a request. There's a desire to have some translation from of our transcripts, what we're saying here, from English to Spanish, so that the Spanish-speaking people can get more out of this. So if you're interested in providing some volunteer translation service, please go ahead and send an email to us or contact us in some way, and we'd be very grateful for that. So that's a new thing I didn't mention last time. I wanted to bring that up though. And finally, one more thing. We'd like you to make sure to fill out the survey to let us know how you feel about this course, whether you're getting a lot out of it, and what we might be able to do better. So if you could go to this link, okay, here's how you go and fill out the survey. Under feedback, there's this place that says click here. If you could just click there, then you can fill out this survey. So please don't forget to do that. Again, we'd be most grateful for anything that you do there. Okay, so I gave you this project last time. If you forget the project, go back and look at my slides that I put in Dropbox last time, where there's a detailed description there. Essentially, it's like you're designing a computer game where you have to shoot some projectile, some kind of light, ball lightning, they call it in the game, and hit some kind of monster. And I let you guys struggle with setting this up for a little bit. I really wanted you to figure out what kind of angle you need to fire the gun at to get the monster, and then be able to chart out a trajectory for the ball lightning. Okay. So I also asked you to try to follow all the steps that I had set up last time. Namely, I want you to draw nice diagrams. And I've made an example of what I used to make my computer code. So let me actually close my slides here and show you more of my code. So pretty soon today, I'm just going to put my, at least my basic code that I started putting together into your Dropbox folders. So you can, if you're stuck, you can use that to proceed. We're going to break out in breakout sessions here in just a second again. But let me show it to you first. Here's my code in Jupyter. I typed it into Jupyter, and maybe it would be helpful to open up a PDF of my slides so we can look at this. Okay, so I had a really basic sort of flowchart diagram that I drew last time. And started adding details, and I've added even more details now that I'm actually typing stuff in. So what I really envision getting is a graph of the height of the ball versus its horizontal position. Okay, so I'm going to have something in my code that just makes that kind of graph. So I decide to make a box in my flowchart diagram that indicates that. It's going to be one step. With the little bit of algebra that I did last time, that we all did together last time, we figured out that if we want to get the angle that you shoot the ball lightning at, you want to get the angle, you need to know several things. We told you in the setup that we'd be given v0, the initial speed. We, of course, know the acceleration due to gravity. And we need to know the position of the monster, so the delta x and the delta y of the monster. So that's what I needed to do. So it might be useful to draw something here. So we start here, and we need to substitute all of that into the equation that we got. So go back and look at the slides that I put in Dropbox to give you a reminder of that equation. It was something that required that we use inverse trigonometric functions as well as a solution to a quadratic formula. And we'll have a segment of the code right here that does that. Okay. And remember, there are two solutions. It's generally two solutions. It's a quadratic formula that we need to solve. And so we'll have two thetas. So I'll say maybe theta 1 and theta 2 relate to those. And at some point, we need to ask which one of those thetas we actually want to plot. So probably at some point, we want to do both of them. But we need to at least have a flag in the code that says which of these you actually want to plot. Okay, so once we get theta, then we know how to get y versus x. We just go back to the formula. This should have a v0 on it, by the way. And plug the formula back into, plug theta, whatever theta we got, back into the formula. We know what x is at any given x, okay, and that tells us what we use for y. Then we use the code that we set up to make a graph to actually make a graph with our final result. So let me go through my code and out these various elements as I step through here. Actually, I made a big deal about how everyone should heavily comment the code. So one nice thing about Jupyter is it has this markdown system that allows you to put in a lot of text. You can actually make it look kind of like just like a report that you would write in class, just with calculations in it. So let's call this ball light mean, learn how to spell. All lightning game.
Hi, sorry to interrupt. Sometimes you're a little fuzzy. Do you have a mic that maybe you're covering with your fingers or something?
I don't think so.
Okay, all right.
Let me position myself for a second. Is this okay?
No, it's okay. I don't know what the others, if they struggle with the same. Maybe I'm just hard of hearing myself.
We'll let you know if it gets fuzzy again.
Okay. Oh, all right.
Okay.
Sorry about that.
It's okay. Okay, so let's go back to my slides and my code. Okay, here's the flow chart that I set up. Okay, and I'm comparing that with my computer code. So we're making comments here. So I make a title. See what I did here? I said cell, and I changed the cell type to markdown. Okay, markdown means that it's now something that's just going to be like text. And to make a big title, I put 2 hash tags like this in here. And now I'm going to insert a cell below that. Oops, I didn't do that. Okay. And let's maybe make this a description of what the code's going to do. Okay, so maybe start with something simple. Game to figure out how to create monsters. Okay. And just some tips. You can make kind of a bullet list of maybe more details. Okay. Let's say input position of monster. Okay. Input initial speed.
Getting a little fuzzy there.
Sorry, this didn't happen last time, did it?
Only for a couple of seconds, and then you come back to it.
I'll try leaning forward more. Everybody hear me now?
Yes, that was very clear.
Okay. So input initial speed, and that angles, and maybe plot all lightning position. And then if I click return, all of those stars turn into bullet points. So it looks very nice. Another way to do commenting is with these hashes like this. So I automatically import the various libraries that I tend to use. I like to define my own functions to simplify the formatting. So I define a function called square root of x, remember the colon, and it returns square root of x, just so I don't have to write np dot square root every time. So that's what that is. We can even make a comment here. Define square root. Okay. Then maybe make a new comment to explain what the next step is. So I'm going to look at my chart that I made, and I see that one of the cells says I need to create a graph of y versus x. So I'm going to make a function specifically for that. Okay, I'm going to give it a name like draw graph. And it's going to take an x and a y. So these x and y are actually going to be lists of points in x and lists of points in y. And it's going to take a minimum x and a maximum x to tell me how far to plot. Sol is going to say whether I'm going to plot the solution that corresponds to what I call theta 1 over here or theta 2. And so I'm looking at this step right here. Okay, and actually let me make sure to document all this. So x equals horizontal coordinates of ball right here. Y is the same thing, except it's vertical. Okay. So everybody should have stuff like this in there, because otherwise you stop being able to figure out how to use it. Maximum.
Hey, Ted, do you have an external mic? I mean, I'm still struggling a little bit. I don't know. Alex, are you still struggling with it?
X's.
Every now and then, yeah, it kind of gets fuzzy
Finally,
for a couple seconds and then
Sol
fixes.
is which
Hey, Ted, can you hear us?
theta 1 or theta 2. Okay. The Sol will be equal to either a 1 or a 2. Okay, now you see what enters into draw graph. I'm using plot, PLT, plot, I call it PLT, which I've imported from matplotlib. So that's this line right here. PLT dot is referring to that up here at the top. So then PLT dot plot creates the basic plot. Okay? And then I can label the x-axis and label the y-axis. I'm going to do very unimaginative labels here. So x position and y position. And then I can give a title. So plt.title, I put in there, becomes the title of the plot. And we'll see how this gets used down below. And plt.x then tells me what the limits of the axis are going to be. So I want to go from the beginning of the trajectory, and I want to go a little bit beyond the end of the trajectory because it would just be easier to visualize in that case. And so I'm going to go from x min to something like 1.5 times x max. Okay. Then we go back over to, okay, my flowchart isn't exactly perfect. I could involve more details here, but this is just to give you an idea. Now I actually have to do this step right here, substituting V0, G, and delta X, delta Y to get the two theta solutions. Okay. So for that, I'm going to make a special function that takes a particular V0 and takes this particular Sol and eventually calls draw graph to make a plot of the trajectory. Okay. So let's go through what I need to do exactly here. So actually, some of what is inside of this function corresponds to this box in my flowchart. Namely, I'm specifying v0 and the value of g right here. We're going to give the monster some position in x and y. So delta x is the x position of the monster. Delta y is the vertical position of the monster. Okay. Then I want to make a line going from the muzzle of the gun monster and following the trajectory of the ball lightning. So for that, I make a list of x points, okay, starting from 0 and going to del x, the position of the monster, okay, and in steps that I'm going to make equal to 0.01. Okay, so I've got the list of x points that I'm interested in. Now I'm going to actually figure out what those two solutions for theta are. So we go back and look at my algebra that I did last time, where I wrote out expressions for theta 1 and theta 2. Okay. Compare there and note that all I've done is transcribe those equations into Python operations. Note that I use np.arctan, that's the inverse tangent, so that gives me a theta. And I have one solution corresponding to a plus sign in front of the square root, and one is right here, and one corresponding to the minus sign. So if you didn't get these last time, compare what I have here with what we actually wrote in the slides last time, and make sure that you can put them into your own code. Some people had a little bit trouble getting these operations to work out. Then what I do is I set theta equal to 0, just because whenever I'm working with a variable, I like to give it an initial value. You don't really need to do this, it's just a habit that I have. And then I'm going to check whether solution is equal to 1, in which case I want to take the solution with the plus in front of the square root. So I say I use this control sequence that I discussed in the first or second day. Do an if statement, and if solution is equal to 1, set theta equal to this theta 1, and otherwise set theta equal to theta 2. Then I'm just going to print it to make sure that the thetas that I get make sense. Okay. Then I'm going to actually plug in what I get for all these x's and what I get for the theta into an expression that takes the list of x values, I got it here, substitutes them into this formula, okay, over here. So compare this formula right here with what I've written right here from our previous little bit of algebra also, and convince yourself that they're the same thing. Note that I used a tangent argument right here, that tangent is inside the math library up here at the top. Okay, and then I'm going to draw a graph. So the minimum of the graph is going to be the minimum of the x points, and the maximum is going to be the maximum of the x points. So when I do the plot, it's going to go up to about 1.5 times x max. Okay. So maybe we should add some comments here. Here we calculate the actual trajectory. And probably, if I weren't doing this live, I would fill in a lot more detail here. I'd fill a lot more detail everywhere. So now I send draw graph. Okay. I send draw graph the x and y lists that I have there. I send it the minimum x and the maximum x. And I send this a solution that I want to look at. Now actually this, I left some things here that aren't quite sensible on purpose so that you can see the process of building up a code like this in real time. When I first went through and made this code, I thought at this stage, maybe in the draw graph function, I'll make a decision inside that function whether to draw a graph for a solution one or solution two. But then you see down here, I never really actually used that. I kind of changed my mind halfway through writing this. So this sole argument doesn't actually do anything. Maybe I'll put a note here. Okay, I didn't change it because I was doing this very quickly. I actually make the decision about which solution to use within this draw trajectory function. Okay. And that makes it very convenient because I can draw both solutions on the same graph by just looping over both solutions. So that's what I do here. Loop over both solutions, solutions 1 and 2, and draw curve float. So I'm going to make a list called Sol's list. That's the list of possible solutions, either 1 or 2. I'm going to pick some velocity here that I'm interested in. And then here I have a for control structure that says for S inside Sol's list. It's going to do draw trajectory for each one. So it sends vel and S back up here to draw trajectory. So the initial V0 is going to be whatever I call vel down here. And I just decide to make it vel. And then I have a function plot legend that puts a legend on top of that plot. And hopefully that still works. Okay, so it works. I just need to run everything again. So these are two solutions that I get when I have velocity equal to 12. So looking at what you guys were doing on Slack last Tuesday, it looked like a lot of you got this. Now we have set it up, I can usually just change solutions and see what happens. If I make the initial velocity faster, note the characteristics of these solutions. One of them is like I just shot it like a straight line drive bullet right from the gun to the monster. The other one, it sort of pops way up and then comes back down again. Okay, so I have two ways of hitting the monster. One's to point the gun directly at the monster and shoot it in a straight line, or nearly a straight line. The other one is to try to pop it way up and have it come right down on the monster's head. What happens if I make the velocity smaller? Velocity. If the initial velocity gets too small, eventually I get some kind of error. Okay. Why does that make sense? Does it make sense that I get an error? Well, if you just think physically, it should make sense. If I imagine I'm lobbing a baseball at something, if I lob it too slowly, it doesn't matter what angle I throw it at. It's just not going to get to it and try to shoot. Okay. So eventually, we get to an initial velocity where these functions like arctangent don't give a meaningful result. So really, what we should do is put in a test inside of this code up here to make sure that there is a meaningful angle, okay, and then return some kind of message if it's not, so we can have it so that it says initial speed too small or something like that. There's where the velocity line. Of course, all of this, I'm thinking about meters per second. We should probably be good physicists, put units in our graphs. X position in meters, Y position in meters. If I do d6. The faster the initial velocity, the larger the distinction between these two types of solutions. Okay, another thing I can do is iterate through several different choices of velocities for a single solution. So let's look at just the theta 1 type solutions, essentially these pop-up type solutions. I can make a list of different initial velocities I'd like to look at and compare on the same graph. Okay. So I'm going to iterate through a bunch of different velocities using this for loop and make another legend indicating what the different velocities are. And the result is something like this. Actually, I include one more thing here, which saves this graph as a PDF file. So if I want to give it to somebody else or put it in a PowerPoint slide presentation or something like that, I can do that. So that's the command for that, if you want to try that. Okay. We could make these even more different, just to have fun with this. And set it up to automatically change the legends. Here's what I should do. Okay, so I'm going to put this, what I've done here, in the project one folder on Dropbox, so people who are stuck on it can take this code and use that. What would be great is if everybody sort of expanded on this and tried to make it nicer. So there's a lot of awkward stuff here. Like I still got this soul up here. You can get rid of that. It needs to be commented much more. You can try making different kinds of graphs. So maybe change what the curves look like. We can make tables of graphs. And so we maybe have one graph that's like different velocities, one that's like different solutions. Okay. So there's actually a lot that we can do. Other than that, that's really the end of project one. Before I leave it behind, though, let me maybe suggest some extensions. And I can help everybody with these things as time goes on if people are interested. So the way I set it up, I gave you an initial velocity, initial speed, that is, and I asked you to find the angle that you need to hit the monster. You could ask for an initial angle and return an initial speed instead. So that's one minor modification, fairly minor modification that you can use to get exercise on setting up this kind of program. It might be interesting to figure out how the positions depend on time. All you need to do is go back to the original set of algebraic equations that we had relating x to time and y to time. Now you have the angle that you need. You've got the initial speed, the initial angle, the delta x and the delta y. So all the stuff that you need to plot those graphs and see how does the x position change with time, how does the y position change with time, and so on. Other relevant questions you might want to answer are things like how long does it actually take for the ball lightning to hit the monster? Okay, we've got one trajectory that sort of goes in a nearly straight line for the monster and another one that pops up and goes down. Which one is faster? Which one is slower? So for the fourth bullet down here, basically an extension to the second one, you want to find what is the x position and the y position as a function of time, basically both of these. But ultimately what you can do with that is you can make an animation showing the ball as it goes toward the monster. So you can actually make a movie showing the ball go boing and coming back down, sort of like what I showed originally when I described this project for you guys. Okay, and here's the function. There's actually a link here to some documentation for how to use that. So if you're interested in trying to pursue that, just go to my slides, which again, I'll put in Dropbox here in a second, and click on that link and see if you can set up the animation. And I'd be happy to see if people can get that to work, because that's fun. And there are many other things that you can do, but these are just my suggestions of how to take this and push it further. Okay, so we'll go into breakout rooms again here in a second. But before we do that, I want to describe another project that I have in mind for everybody to work on. I can again provide some help. Having to do with collisions. So I can come back to this later as people make progress on the first project or as they start to work on this project, but let me just introduce it first. Okay. So to provide some motivation, let me remind you of some of the nuclear/particle physics topics that I introduced the first time I was lecturing. So one thing we like to do to understand how particles interact and how they're made out of is we like to smash various particles together at very high energies. Okay, and here in Virginia, we've got this machine called CBAF here at Jefferson Lab. There's, if you look carefully, a ring, an oval-shaped ring like this. This is Jefferson Lab looked at from above, from an airplane or something. Okay, and that oval has electrons going around and around in an oval shape. And eventually they come out right about here. And if you look closely, you should be able to see three circular mound shapes. One here, and one here. Those are all fixed target detectors sitting underground. And this beam of electrons eventually comes flying out and gets deviated into one of these detectors where it smashes some target like a bunch of protons. And then there are a bunch of detectors surrounding the target that detects what comes flying out. Okay, so these are scattering experiments involving scattering of elementary particles. Here is a more schematic diagram. So if you just imagine this thing up here, this oval-shaped device up here, embedded underground right here, then that's what I'm talking about. So underground is this thing here, and then this A, B, and C, that's these bumps right here. Okay. And theoretically, a lot of what we do is just trying to figure out what we expect to happen when the particles that come out here, the electrons, collide with these target particles. So it's a big collision problem. Okay. The basic ideas start with what you learn in intro physics classes, just conservation of energy and momentum. That's a big part of what we do here. Of course, there are other complications, a lot of other complications, really. But in particular, we have particles that are moving close to the speed of light, so we have to deal with relativity. So it's relativistic momentum and relativistic energy that we're mostly thinking about. And we've also got quantum mechanical effects. But the basic idea starts with conservation of energy and momentum as you learn it in say, high school physics. Okay, so again, in a more cartoonish way, what we have is an electron coming in and a proton coming in, something like this. Remember, the proton is made out of quartz, so I sort of made a cartoonish depiction of that here. So here's what it looks like before. Then the electron scatters from the proton and it explodes into a bunch of new particles created in the collision. That's what POW means. A bunch of particles come out along these lines, and the electron gets deflected and goes out into some detector. And we have to make sure that momentum and energy and all that stuff is conserved. Okay, so let's build up to that. Okay, it'll take a long time to build up to that, but the main idea is to give you some motivation, something to aspire to here. Let's look at what you would see in the very beginnings of physics. You've got momentum, usually denoted by a P. P is equal to mv, the momentum of a body with a mass m, and kinetic energy is 1/2 mv squared. Okay, I'm going to think about everything as taking place in one dimension. So we have objects scattering along a straight line. Okay. And when we talk about momentum and energy conservation, we say that the momentum before is equal to the momentum after. And if it's an elastic collision, then we also have kinetic energy conservation. So that would be like really like billiard ball scattering, where you don't lose any kinetic energy in the process of the collision itself, or maybe scattering by marbles, if you've ever played marbles and knocked them off of each other sitting on the floor. Then you have both P before equal to P after and K before equal to K after. Okay. So the next project is to essentially describe the collision in one dimension of two marbles, and you can work up from there to something more interesting. I'll talk about how you can build on that to get something more interesting, but let's do the basic thing first. Okay, two marbles, you can think of this as the very basic type of collision experiment. So this is the step 0 on the way toward the Jefferson Lab experiment. Okay, so before the collision, we've got two marbles. I'm going to call it M subscript B and M subscript R for blue marble and red marble. Okay. And the momentum before is just the sum of the momenta of the individual marbles. Okay. Note that these velocities can be positive or negative, depending on which direction you take to be the positive direction and which one you take to be the negative direction. And their kinetic energies are also just the sums of the kinetic energies of each marble. Okay, then afterwards, how there's a collision, and then the marbles look like this. They're going away from each other if they were originally going toward each other. And I'm going to say, after the collision, we'll denote the momentum, the total momentum of the system by P prime. So again, it's just the sum of the individual momentums after the collision. And the kinetic energy by K prime. And again, it's just the sum of the kinetic energies after the collision. Okay. So momentum conservation says that these total momenta are the same. So P has to equal to P prime. Total momentum is the same before and after the collision. Okay. Now we've got basically two algebraic equations. Okay. And what I have in mind for a project is a situation where you know the momentum of the blue marble originally, you know the momentum of the red marble originally. Okay. And you want to figure out, and you know their masses too. You know MB and MR. And you want to figure out what is VB prime and what is VR prime, the momentum, the speeds after the collision, the velocities after the collision. Okay, so we got two algebraic equations, two linear algebraic equations, and two unknowns. So we essentially just have to solve a system of two algebraic equations. Let me go through the steps of that so that you don't have to. But this is the stage in the setting up of the project where you write down what you know, what equations you've got, and assess what physical principles you need. Okay, go back to my guidelines. Okay, so we're going to say momentum before is equal to momentum after. Okay. And then all I've done here is rearrange this equation so that I've got MB multiplying something on the left side and MR multiplying something on the right side. Now I'm going to set that equation to the side for a second and look at energy conservation, kinetic energy conservation. Okay, it's the same kind of equation. I'm using the expression for the total kinetic energy before and the total kinetic energy after. Okay, I can get rid of all these 1/2s because they appear on both sides of the equation. And then I'm going to move this VB prime squared term over to the other side. I'm going to move this VR squared term over to the other side, like that, and I get this equation. Put a star next to it. Okay, and then I get a pair of equations that I can deal with very nicely. If I write this VB squared minus V prime B squared as the product of two quantities in parentheses, VB minus VB prime and VB plus VB prime. And I do the same thing for VR prime squared and VR squared here. Why is that nice? Because I already know that MB, VB minus VB prime is equal to MR, VR prime minus VR in this equation. Okay. In other words, I have this. Okay, so I can basically get rid of these factors and get VB plus VB prime equal to VR prime plus VR. So now I have an equation for VB prime in terms of VB and the VRs. Okay. Okay, now all I need to do to get an expression for, say VR prime in terms of stuff I know is substitute VB prime back up into this equation up at the top, and that's what I've done over here. Up here at the top, I've just substituted this up here and rewritten it over here. And then I just rearrange terms so that I can isolate VR prime. And then I just need to divide by VB plus VR to get an expression for VR prime, the speed of marble, of the red marble after the collision in terms of stuff that I know, namely the speeds of blue and red marbles before the collision and their masses. Okay, so that's what I get over here. And then I can just do basically the same set of steps to get VB prime, the velocity of marble B after the collision. Okay, so if my computer code, if I have a computer code that can take the mass of the blue marble and the mass of the red marble, as well as the velocity of the blue marble and the velocity of the red marble before the collision, then I have equations that can return the velocity of the red marble and the velocity of the blue marble after the equation. Okay, so project 2 is to take this setup that I made and make a program that calculates well, once you can figure out what the velocities are, well, you can figure out when the marbles collide. You don't even need to get VB prime and VR prime to do that. Okay. Since you know their initial velocities, if you say their initial positions back here, in this picture, if you say that this marble starts at one point and this marble starts at another point and they have velocities pointing toward each other, then you can figure out when they collide. Okay, and then if you can figure out their velocities after the collision, then you should be able to make a graph showing the trajectories of these marbles. They come together, they meet at a point, and then they go apart at some velocity. Okay. Okay. Discard annotations. So maybe let me show you what I did for that. So here's my Jupyter notebook showing a calculation of the collision of the red and blue marbles. Okay. To their positions, and they have some initial velocities. You see the red marble is moving pretty slowly since its slope is small. The red marble is moving pretty quickly. If I set the clock to be at 0 when they start moving, then at 10 seconds roundabout, they meet one another, collide, and then there's an exchange of momentum between the two marbles. The red marble goes out in a certain speed and the blue marble goes out in a certain speed. So your first task is to get a plot like this. Then you can do other fancy things like make animations. So actually, let me show you an animation that I made in Mathematica. And also do this in Python. Okay, so I've got a dark gray marble. Dark gray means that it's more massive, and a light gray marble. Light gray means it's less massive, and I'm going to play this animation to show what happens when the dark gray marble hits the light gray marble. And there you go. There's a transfer of momentum between the two marbles. Okay, so now we might be getting a little bit ahead of where everybody is, but just so you see where we can go. Can everybody hear me now?
Yes, can you hear us? Can you hear us, Professor?
Hey, Ted, can you hear us?
Make that kind of animation. If you want to make this more reminiscent of a scattering experiment, you can set it up so that you have a distribution of possible initial velocities and positions. In an actual scattering experiment, you don't know exactly the position and velocity of the balls. But once you study how to make distributions. Once Raul starts lecturing, then you should be able to do that. And you can make the collision relativistic if you know the equations for relativity. If you don't get there, that's fine, but just to give you an idea of where you can take this if you spend a lot of time on your own, I can show you what happens if you use equations that make the momentum obey relativity and the energy obey relativity. One thing that you'll learn once you take classes on relativity is that if things are moving very fast, they start to look like they're squished. They start to look like pancakes like this. So here is a ball that's moving to the right very quickly, and its extension in the direction that it's moving is squished down so that it looks kind of like a pancake. This ball is just sitting there, so there is no such effect. So the exact same scenario as above, but now with relativistic speeds, looks something like that. Okay, so I think what we'll do now is again break up into breakout rooms. And the first thing is people should continue to work on project 1 to the level that they're comfortable. So feel like you've gotten everything out of project 1 that you can get out of that. Go ahead and do that. Just note that there are many things that you can do beyond what I've shown here, and it would be nice if you tried to do them. So again, making animations, making different kinds of graphs, figuring out different ways to organize your graphs so as tables of graphs. Those are all fun things you can do. And of course, we'll be here to help you guys with that. But once you get bored with that, feel free to move on to the next project, and we'll also be here to help you with that as well. Okay. So any questions before we move into breakout rooms?
Can you hear us?
Ted,
Okay. I think we'll have, what we've decided is that we'll have one breakout room.
hey Ted, can
Hey,
you?
somehow my sound went off.
Good. Yeah, we've been trying to catch you for a while.
Sorry.
It's okay. It's just a little. It's gonna be funny on the video because we were like, "Hey Ted."
Somehow, for whatever reason, my sound just randomly turns off, and I don't quite understand why.
It's okay. You were on a roll. It's okay. So now that we're back together, yeah. So we were thinking about having two sessions, one in Spanish and the other one in English. So I think what we can do is stay in this one for English, and then go to another breakout session where Juan and I go with Spanish, or if Connor or Alex or somebody else want to practice their Spanish, you're welcome to join us. Or Greg.
Right. In principle, we could have more than just 2 breakout rooms too, right?
Yeah, we can have multiple breakout rooms. Yeah.
Okay. I'll just keep this one open, and if somebody wants to, so you want to make, say, breakout room 1 be the Spanish?
Yeah, we could do that. Sounds good. Also, we have other languages, right?
Right. Then breakout room 2. If somebody wants a different language,
Yeah.
feel free to request it. And if we have somebody who speaks it, we'll
That's right.
make a place for that.
So,
Okay, so breakout 1 will be Spanish, and breakout 2 will be whoever wants to take charge of that breakout room for now.
sounds good. Juan, do you know how to get to the other breakout room?
I guess that I have to go out and now enter to a breakout to a session 1, or I don't know.
Good. Do you want to make an announcement in Spanish telling people to go to the other breakout room, to session 1?
You mean here?
Yeah.
Buenas tardes a todos, espero estén muy bien. Bueno, ahora vamos a empezar la sesión en español de discusión y nos vamos a ir a la sesión 1. No sé si ellos tienen que seguir alguna instrucción especial para entrar, Raúl. No sé cómo sea para ellos el cambio de ambiente.
Ellos deberían ver un enlace justo al lado del video. Entonces en el video van a ver un enlace que dice sesión número 1. Si se meten allá, vamos a estar allá en un minuto.
Ok,
Ok,
bueno, creo que es eso, ¿no?
eso es todo. All right, sounds good. So we'll leave you to this and we're gonna leave.
Okay, I'm going to disappear for just a few seconds or a few minutes so that I can put all this material in Dropbox, my slides and the code and so on.
Sounds good. Maybe, is there any questions from TAs that they've
Yeah,
looked at, perhaps we want to address with everybody together before we go off?
Yeah,
Tengo
there
un
were a couple of stylistic questions. One was from Amar Abushakur from Amman, Jordan. He asks, is there, back on the projectile project, is there a reason why G was assigned inside the draw trajectory function?
Not really. In fact, probably if I did this again, I wouldn't do that. So that's the best answer I have for the moment.
Cool, cool. And then we have another one from Dmitry Kalinichenko from Sammamish, Washington. He asks, why did you use Numpy instead of math for the arctan and square root functions when calculating the theta values? Is there a difference or just personal preference?
That was just personal preference for me. I used the one that first came to mind when I was coding. Maybe other people have more specific reasons to use one or the other.
And I think that's all that I've found.
So in fact, if I were to do this again, I would probably make del x and del y arguments of draw trajectory rather than. So del x and del y are the positions of the monster. As I go on, I realize probably I want to change that. So I purposely show a sort of half-written code here so that people can see the code being written as in real time through the process. There are plenty of things like this that could be improved upon. Everybody still there?
Yes.
Yep.
Okay. Make sure my sound is off. Okay. So shall I put these materials in Dropbox and then come back in a second or a minute or two? Good. And everybody knows how to get to the breakout rooms and so on. And also we of course still have Slack.
To answer Lucas's question from Santo Andre, Brazil, sorry, but which is the breakout room for people still working in the first project, or should I use Slack to ask my questions? For the first project, Slack would be easiest.
Additionally, a question from Guri from Kosovo. They asked, how was Sol equal to 1 equal to theta 1, and how do we know the solution is 1 beforehand? We didn't know it was 1 or 2. We are using 1 and 2 as identifiers so that we can select which theta we're looking at. So when we get our solutions, we can put them where we want. So 1 and 2 are not the actual number equal to Sol. It's more of like a true or false type of thing.
Okay. So I've put the slides for today in Dropbox, as well as that Jupyter notebook for the projectile motion. And it's all in a file called Project 1 or Project 2. Actually, I should probably put projectile into Project 1 because that's actually Project 1. Okay. I'll just put it in both folders in case people get confused. So the slides are labeled July 2nd. And notice that there is a link. Let me share my slides here. Notice that where it talks about the animation function, you can actually click on that and go to a page that tells you how to use that. Okay.
I'd like to take a quick moment that if you're still having a issue installing any of the Python formats, it might be easiest to use the link provided by Connor previously and go to repl.it. It's an online program that allows you to code without having to install Anaconda or any of the other programs that we've went through.
We've been getting a few questions about incompatibility between the file and what people are using. There's an easy way to fix that. It's most likely because the file you've downloaded is a Jupyter notebook. So you're going to want to have to open it up with Jupyter and then go to File in the top left, down to Download As, and in the Download As subsection, you should see Python and in parentheses .py. That's the type of file you want to download if you're using something else like Spider or whatever.
We should probably re-upload a different version of it just as a .py. You do that for them already. I think some people don't have Jupyter.
Okay. Okay, so I've put a .py version in Dropbox.
So there's a question from Alex Miller coming into the Rise chat, who's asking if you can make changes to the code in Dropbox. No, not usually. I don't think that that's a feature that Dropbox has. You're going to need to download the file to change it. We have a question from Eduardo asking if they're going to grade the project. I think the answer is no. That is just to learn from.
Yeah. I mean, we can certainly look at projects and make comments and stuff like that.
Yeah. Do we have a way for them to, like an established way for them to send us their code, or?
That's a very good question.
Make a Slack channel for it, maybe, or they post a GitHub link or something like that.
Yeah. And there's always individual direct messages on chat, on Slack, that is, right?
Yeah.
If you don't want other people to see your code or whatever, you can just send me or Raul or the TAs directly a chat with your code.
An interesting question, perhaps for you to answer, Professor Rogers.
Mm-hmm.
From Jose Cochegros from Mexico. He asks, in real particle collisions, the directions of the new particles created after the collision is given by some law, or as is common in quantum mechanics, it has to do with probability?
In quantum mechanics, it would be a probability. So in quantum mechanics, we wouldn't be able to say that, well, we wouldn't be able to say that the incoming particle had a particular position and speed at the same time. If you've heard of uncertainty principle, we'd have to say that there's kind of a lump of probabilities for the particle to have a given position and a given speed. We say there's a wave packet coming in, the wave representing the probability to find the particle. That's kind of why I suggested converting this into a probabilistic collision once you figure out how to get the basic Newtonian collision to work. So I noticed a lot of people got confused with, sorry, let me just catch up with what people are saying here. Okay, people got a bit confused about the projectile problem when you put in certain velocities in certain positions and you got some kind of error or something. So of course, if you think for a few minutes, you should realize that if the velocity is too low, if the monster is too far away from the gun, then it's just not possible to hit the monster. Okay. And if you really want to make a good computer program, you should test that there is a solution before you try to do the calculation. And so what happens if you choose a position for the monster that's too far away, or a velocity that's too small or something, the way that'll come into your calculation is that you'll find that you have a negative under the square root sign. So the best way to deal with that is to set up an if statement that says if the discriminant, the quantity under the square root sign, is negative, then print out something like not possible or monster too far away or something like that, and then stop the function. Okay, then you know what's going on. You haven't really made an error. You just are not able to hit the monster. Okay. Okay. Lots of good questions in Slack. Okay, good. And note that there isn't, if the question is just how do you hit the monster, there isn't a correct solution, right? There are two possible ways to hit the monster for every initial speed. Although, in the past when I've assigned this as an exercise, let me show you my slides again, just a second. So here's what that computer game looked like. This is an actual computer game, by the way, or I think it's for smartphones. Although it's not one that I've ever played. I took these pictures from a friend of mine. If you've got a monster like this one sitting here, this little guy sitting right here, and you've got a trajectory like this, and you guys now know that there should be another trajectory. Now you see the monster is standing on this treasure chest thing. What if the other trajectory goes like this? Then if you've got, in this path that I'm showing you here, so what if you, I don't know if this is the case, but say that you calculated and the other trajectory went something like that. Okay, well then you might want to say, well, that's going to hit the treasure chest. So another way that could expand this program is imagine a box for this treasure chest shape, and ask the question, does the trajectory that the user enters intersect with the treasure chest? And if so, you might say, well, that's not acceptable, it's going to hit the treasure chest. That means you have to figure out different points along the path of the all likelihood, other than just the final one and the initial one, but points in between. So someone's just pointing out to me that there's a typo on the contact us part of the website. It says Python for physics at odu.edu. Of course, that should be Python.
Hey Ted, can you send that link over to me? Is it something that distance learning manages?
Excuse me?
Is the typo in the link that distance learning manages?
I'm not sure. Maybe somebody else should chime in because I'm just reading from somewhere else.
I think Raul controls the site. I'll talk to him about it, and he'll send a link if you guys are in control. I'm not sure.
Okay. Yeah. Just in case if that's something that it's on our side, we'll be glad to take care of it.
Cool.
Okay, so before we run out of time today, I thought I'd show some other stuff I've been doing to try to extend that projectile motion project a little bit. Maybe I'll...
Just a warning, we have 4 minutes left.
That's right. That's all I need. Okay. So if you look here, I decided I wanted to plot the x position as a function of time for different solutions. Okay, there's no acceleration in the x direction. There's just an initial velocity. So both of those solutions have a straight line shape when you plot x versus time. Okay. And then I've done the same thing for the y. Or also you see that just as in my previous example, I set the monstrous position to be at 1 and 4 meters in the x and y directions. And of course, these lines then just go up to 1 meter. Okay. You see that one solution takes more than twice as long as the other solution to get there. And then I do the same thing for the y direction. You can see a blue curve. It's a little bit obscured by the orange curve for solution 1. There's one solution that arches way up, reaches a peak, and then comes back down. That's like the pop-up solution. And there's another one that's more or less like a line drive type of solution, this blue one right here. And both of them go to a end at a height of y. Okay. With again, one taking about 2 seconds and one taking about half a second. So the next thing I want to do is turn this into a animation inside Jupyter. I'm only about halfway through so far, but I can share this with people as they look in progress. Okay, I probably used the last 4 minutes or so, like the last 2 minutes. And I just wanted to show you what I was doing there. So of course we'll still have access to Skype after we hang up today, so feel free to ask us for help, ask me at least. That's good for everybody. We're going to have to stop pretty soon. So if there are any really urgent questions before we go, let me know. Somebody's asking if you need to know the relativistic stuff. No, you don't need to know it. You don't need to do anything here, right? So I'm just giving you in these slides options for how you can take a very basic type of program and play with it if you happen to have the information that you need to do that. If you don't, then don't worry about it. There are many things you can do. You can play with how you present these results, make nice graphs. You can move things from this one-dimensional type of collision into 2 dimensions. Okay, I just want you guys to feel motivated to try things yourself, come up with different ways to do things that I haven't talked about. Okay, so don't be intimidated if you see something here that that is very unfamiliar. I just don't want to hold anything back. All right, so we're at the 3 o'clock mark, so I really should probably hang up now. Does anybody else who's online want to say anything? Any announcements or anything before we go today? Any technical things?
I believe one person was asking for the information for how to be one of the translators. If you just email at pythonforphysics@odu.edu,
Right.
with the subject line about your interest in being the translator, then we'll get back to you on that.
Okay. Anything else?
Anybody who's looking into doing really like sophisticated animations for their project might want to look into Pygame. I'm not particularly experienced in it, but I have done something with the Collisions project in it, and I think that you could do some really interesting things with it that way. But I don't think that we can help you with it. So that you're kind of on your own with that. Yeah.
Okay. So it's 3:01 now, so I guess we should probably hang up. Thanks again to everybody for their attention and their enthusiasm.